Now today we have the two eminent speakers. So first one is the Professor Devendra Kumar, Department of Chemistry, Guru Jambeshwar University of Science and Technology, Hisar. And another speaker is Dr. Rajendra Singh from Central University of Chemical Science, University of Punjab, Bathinda. Now I am going to introduce our first speaker, Professor Devendra Kumar. Now, presently, he is working as a professor in the Department of Chemistry, Guru Jambeshwar University of Science and Technology, Hisar. He holds the position of Director of Dr. APJ Abdul Kalam Central Instrumentation Laboratory and Coordinator, GIAN Program of JU, just Hisar. And he has also served as a chairperson, Department of Chemistry, Guru Jambeshwar University of Science and Technology, Hisar, and coordinator of DST program of DST, New Delhi. During his professional career, Dr. Devendra Kumar has guided 7 PhD students, and presently 4 PhD students are pursuing research under his guidance. His current research interests focus on organic synthesis, medicinal chemistry, heterocyclic chemistry, and hypervalent iodine in organic synthesis. And he has published over 80 research papers in the peer-reviewed international and national journals of repute. And he has completed 4 major research projects from UGC and CSIR and DST, and he was conferred with Best Teacher Award by Chemical Research Society of India, Bangalore. Welcome, sir.
Thank you, madam. Thank you very much.
With these words, I would like to invite Professor Devendra Kumar to deliver his talk, and he will deliver the talk on NMR spectroscopy. Welcome, sir.
Okay. Thank you, madam. Thank you very much for kind words. So I may directly start my presentation. Is it okay, madam?
Yes, sir. Yes, sir.
मैडम स्लाइड्स विजिबल है?
विजिबल है सर, विजिबल है.
ठीक. So today I am going to give a lecture on NMR spectroscopy. Before taking detail of NMR spectroscopy, I would like to let you know that there are a number of instrumental methods of analysis. मेरा आवाज ठीक है? कोई और तेज करना है?
सर थोड़ा सा लिटिल बिट वो कर दो सर.
तो मैं कम कर इसलिए मैं
हाँ वैसे आवाज साफ आ रही है, क्लियर आ रही है.
Yes. So before going to NMR spectroscopy, let me tell you that there are various instrumental methods of analysis and a number of things. For example, how we are trying to generate the signal which we wish to analyze for different type of the purpose. Firstly, because we are having various types of the radiation, and based on the radiation signal, we are trying to have the different type of instrumental methods. For example, if I say that we are trying to visible electron fluorescence, phosphorescence, and luminescence. Whereas if absorption of radiation the instrument visible NMR and ESR. For scattering of radiation, it is turbidimetry and nephelometry, Raman spectroscopy. Whereas for reflection of radiation, it is refractometry, interferometry. and diffraction of radiation, X-ray and electron diffraction methods. For rotation of radiation, it is trying to analyze various type of the radiant signals. Based on that, we are having various instrumental methods. Besides this, we are having different type of the electrical signal as well, but I'm not going to for this one. I will go ahead with that of Nmr spectroscopy, because the details of Nmr spectroscopy are in such a way that it becomes different. But I will touch number of things where I can try to justify the Nmr spectroscopy. So try to know that what type of the wavelength we are looking for the NMR and other type of the spectroscopy, and the size of the wavelength is also equivalent to what type of your things. And so this is what we can go from your radio frequency to your gamma rays. So for NMR, we need radio frequency, and of course, as we say that ultraviolet spectroscopy and infrared spectroscopy. So these spectroscopy is derived from say violet, red. You can see trying to analyze after interaction with the molecule. Then after infrared after. So that type of spectroscopy is infrared spectroscopy. So this on the head, and similarly for violet also we can say before violet, or before violet may be called as ultraviolet. So based on them we are having the two types of the spectroscopy. Therefore, I am taking this one. And this Nmr spectroscopy is highly valuable technique for identifying CH framework. And not only this, we can know the entire structure. We can read the entire structure of Nmr spectroscopy. And the determination of the structure of natural product like protein, enzyme, etc., they are also helping in knowing that in designing the drug molecule, because how the drug is interacting with the protein and enzyme, and if we can know the structure of protein and enzyme with the help of NMR spectroscopy, then we also know that how the drug is interacting with the protein. But there is a requirement of not only 2D NMR as well as 3D NMR in order to know their folding depends upon the concentration of to know the of the protein. We have to mention that amount what is taken, so that you know in a different concentration of water. So this NMR technique is important biologists and others also. And excellent application of addition today is magnetic resonance imaging, because we say NMR is nuclear magnetic resonance. To know, we are trying to about excellent application in medicine. That is so in that case, and there was the actually image that is being obtained while taking the MR of the whole body. So initially and changed to MRI because the general public may not scare with the word nuclear. So that's why it was called MRI. So now it is very popular, and in most of the cities, and MRI is available. Basically, this is MRI. So if we just start with that, in 1920s, the scientists was able which are having the property of spin and magnetic moment. And if the nuclei is having those property of spin and magnetic moment, then what to do with this? So let's to expose this type of the nuclei in a magnetic field, in a higher magnetic field, the splitting of energy. But in fact, I can say the atomic nuclei are magnet. And what will, but remember, this magnet is star magnet is not in isolation. It is present in the molecule. For example, if we take hydrogen, is behaving a small magnet because it is possessing the property of spin and magnetic moment. So it was in a strong magnet in order to know that there was observation that is on 1950 was actually and the pure cell who shared the 52 actually they are considered as a disk of NMR, and they actually were working independently, and they demonstrated that the nuclei when that is small nuclei which is present in a molecule placed under the influence of a strong magnetic field, under a strong magnet, and it undergoes the splitting of energy level, and with this this may absorb, if we just feed it to it electromagnetic radiation EMR, then there may be the observance of this NMR phenomena. So this NMR means when a nuclei like hydrogen or the carbon or nitrogen 15 or or other nuclei, when a nuclei are actively present in a molecule is placed under the influence of a strong magnetic field, undergoes magnetic radiation. This is how we present in a molecule of certain EMR, electromagnetic radiation. And this was actually observed in 1940, and you see from 1920 to 1940, and then in 1952, finally in 1953, the first NMR spectrometer was launched by a company called Varian Associates. The brief that how it started and the NMR. So this is all basic things you know, because I think the faculty members are there. There may be some students also. So we see hydrogen nucleus is not so the nucleus. This atom, in an atom there is a nucleus, and nucleus contains proton and neutron, and the electron hydrogen nucleus. And when this atomic nuclei which is possessing spin and magnetic field, so then they are randomly oriented, and when they are randomly oriented like this, when they are placing it under the it takes so this is actually better to understand. I read again. So when of a magnetic field which is present in the molecule, not in isolation, so it undergoes the energy level, and energy, we say that was spin state and beta spin state aligned and opposed. So this one to explain about this one, and that a nuclei, if it is behaving as a south pole, so when it is being as a magnet, and if we place it in a bigger magnet where this is the north pole, they are oriented in two way. One is of energy and another is of here. The south pole and north pole, they are repelled. So this is of high energy, and this is that whether those hydrogen nucleates are present in the molecule energy, but it is not so. It has been seen that here that approximately 0.001% the population of the more so the energy between these state energy will increase as in this flow diagram where so the instrument here becomes 300 megahertz. And pi into B node, where B node is your we are in the nucleus. So when this pi is this magnet say that frequency is directly proportional to the magnetic field. So frequency will increase, and if the frequency will increase, the difference in energy between the two levels will also increase. So therefore, you can say there is 0.092 Tesla. So here you find that difference in energy is increased, and is 600 hertz. That can be by help of or lambda, so that we can know that and this is what that spinning of the nuclei under the field. And when comes here with the electromagnetic radiation, the NMR phenomena won't be observed. So therefore, this now next it is consumed. So that is we are now giving see here so that it absorb this one and can go after energy absorption. It can go into this state. So absorbed by the nuclei, which is preceding in axis. So therefore, this will, and then finally it will go down. So it will be we can keep it above this one, and generally lower, but there is also jumping here. We will see that form of magnetic radiation by the nuclei, and it achieves this is the direction of the applied magnetic field. So there are more than 4 also. There are nuclei which are shown here, H1, C30, and the for these nuclei is like 2.68 into 10 is to power 8, and the isotopic abundance is your 99.9. Meaning thereby, I wish to let you know that we are having an instrument, 200 instruments, then and if we are trying to record, because there are multinuclear NMR, we can record not only NMR, C13 NMR, 19 P13 NMR, and even C13 NMR, we always used to say have recorded and if we record F19 NMR on the same instrument which is operating at 200 NMR, NMR, we say that F has been recorded at 188 megahertz, whereas the P31 NMR is at 81 megahertz. So let me tell you here, it all depends on abundance, but it depends upon if ratio in that of C13 is about 1/4 to that of H1. So therefore, we are multiplying the absorption frequency of different of NMR based on the H1, and compare, for example, in F19, you'll find the less is very 88 megahertz. Whereas in P31, the magnetic direct ratio is very less, and therefore you will find it is at 81 in comparison to 200 megahertz. So this is just a comparison only to let you know. Proton H1 NMR has been recorded at megahertz. Report the C13 NMR megahertz. Recorded is 188. With us, that is a broker, and so I would like to let you know that generally the R which is being obtained like this. The certainty is in this way. It becomes very difficult to analyze the such kind of we are as this is so time domain signal which is difficult to analyze being converted into the using so here is the name of scientific provide an equation by which we were able to signal difficult to analyze the domain signal. So these were the controls NMR intensity versus the chemical shift with respect to its your standard disilapentane sulfonic acid whenever so because in D2O they are invisible, but EMS is visible with most of the organic solvent. In D2O it is not miscible. For D2O another standard is low of field. The chemical shift we are generally representing in delta, and this delta is your why I know because we are, and another is your the Nmr intensity. Suppose a signal is appearing at 63 megahertz, then if we record the NMR of same molecule on 300 megahertz machine, this will appear at 315 megahertz. So instead of writing, okay, anyway, so instead of writing the different frequency, if we are trying to get the spectra from different, not only the chemical shift in delta, there is parts for not in hertz. It's sometimes if to report, then mention that at what instrument it has been there. But it is not. We should always try to report in the parts per million. These are the typical the different types. Suppose in between 9 to 10 there is no signal not present. Similarly, from approximately from 6.5 to 8.5, if aromatic compound, and if there is no signal, we will say the aromatic the hydrogen and you will see from your this lower than that of and your different type of your methyl group which are present in the molecule. So a brief idea just to have and desilting of hydrogen. So here I wish hydrogen which is attached to a carbon, and the carbon is attached with, suppose you are a Z, and in order to know that of hydrogen, if by because and this because of the circulation of electron around the nuclei. Therefore, hydrogen is equal to the applied magnetic field minus the local magnetic field generated by the circulation. Therefore, if we do electron density around the hydrogen by any mean, then we'll say the proton gets desilted, and if we can increase the electron density around the hydrogen, we'll say the proton gets shielded. This is actually followed actually trying to differentiate between the chemical shift of all the hydrogen. So we'll see that the is decreased. So based on their say, if decrease around hydrogen, we'll see the I won't take the here factor the affecting the chemical shift in. One can say that the electronegativity, van der Waals desilting, and anisotropy are in majority responsible for affecting the chemical shift of hydrogen. So if the electronegativity is more, suppose if I say if I wish to suppose difference like OH and NH, Okay, or if I will take with an example here, you see here in this example, if I say this is CH, chloro, bromo, iodo, and OH. And if I just go with that of the bold one, that is where the halogen is there. So then, and so in that, this is chemical. So fluorine is more electronegative than that of iodine, and therefore chemical methyl hydrogens, they are better for ppm. So you can see the difference in electron. So if electronegativity is more, the hydrogen gets dissoluted. If it is less, then we will say in comparison to that one, we will say is very dissoluted. So say to dichloromethane and chloroform. Here one chloro is attached, two chloro, three chloro. So of chloro and three with three chloro the hydrogen gets dissoluted. So this is about benzene. There is only one signal. In the case of naphthalene, there are two signals, 4 proton each. In the case of this anthracene, we will find there are 3 signals, whereas in the case of phenanthrene, there are both generally 6 signals are there in this one. Okay, and if we just compare most hydrogens are generally two hydrogen. And what type of interaction? This is van der Waals interaction among the two hydrogens. The close, and therefore they just repel the electron density, and with the repelling of electron density around hydrogen, they get dissoluted. Of course, the amount of less into the in the such type of the fixed molecule in aromatic and also the possible the two hydrogens to each other in that case is also observed. So these are actually other the anisotropy, that how in alkene, alkyne, and the hydrogens are still. So if you remember, the alkene is just like a molecule. When it is kept under the influence of a magnetic field, there is of the magnetic field is generated, and with which having the alkyne. So alkyne is oriented under the influence of magnetic field in such a way that the hydrogen of the alkyne is now at this place in comparison to alkene, and that's why the alkyne proton, which theoretically we molecule where there is your the 6 pi electrons which are circulating and generating. Hello. कोई आवाज आई थी बीच में, इसलिए मैंने तो मैडम कर रहा हूँ, ठीक है। अगर हम ज्यादा एनएमआर एक्सपर्ट बैठे हुए तो फिर मैं इन छोटी छोटी चीजों को स्किप कर दूं। Here, here one can think of various type of the protons and what methyl hydrogens, methylene hydrogen, and methine hydrogen. And if we say, suppose here a R group, this R group and suppose these are alkyl group, and generally we say the alkyl groups are electron donating. If they are electron donating, then one can think of more electron density around this hydrogen methyl hydrogens. If it is so, then the your 0.2 for methine hydrogen is 1.4. So that is the test here, but here. So we were hydrogen, it should be 0.9. In methylene hydrogen, it should be 1.2. And it is 0.4. That is not being shown here in the table. Because, of course, we say that the alkyl groups are electron donating, but attached to a unsaturated system. That is not. Electron donation of the alkyl group is not here in this case, but that the hydrogens are more acidic in comparison to methane hydrogen. Methane hydrogens are than that of methyl hydrogen. Acidity is less in comparison to methylene hydrogens. In hydrogen, so therefore the value which is written here is correct. Compare these three. And this methyl hydrogen and this is that here that the 4 non-bonding electron and 2 electrons. So then the and the circulation is 4 electronegative carbon. Therefore, the electron are more in comparison to the 2 electrons. Therefore, the methyl hydrogens are appearing in approximately 1. Also depends upon what the groupings are tested. 0.7 and 2.1. Similarly, and but the difference between the ketone and this this compound, like so they are circulating in a circle here itself, in a cycle. So the induced magnetic field generated by these electrons in a circle is little more in comparison to these 6 electrons. There is 2 electron. So the difference is only less. So here is your this induced magnetic field generated by 6 by the 2.3 in the case of your this ketone. Comparison of ethylene, your this alkene and alkyne attached with that of the methyl. And in the case of the electronegativity of oxygen and nitrogen attached with that of the methyl group. Similarly, we can also talk about the other hydrogen. Skip this one because or we can briefly discuss about this, that what is the correlation of hydrogen or proton bonded to other nuclei. Nitrogen and your sulfur. So the your nitrogen is more electronegative than the sulfur. So generally, in the case of alcohol, stands for monomeric. That is associated or hydrogen bonded. Then we'll say it is this hydrogen is at 4.5. So general range is your alcohol is 0.5 to 4.5. In the case of coal, this hydrogen may be 15 ppm because generally the range is 0 to 20 ppm in the case of hydrogen. In aromatic alcohol or we say phenols, the range is 4.5 to 9.0. For monomeric, or we say the hydrogen chemical shift attached to the oxygen is at 4.5. In the case of associated hydrogen bond, it is your 9.0. In the case of carboxylic acid, it may be your 10 to 13. So similarly, we can talk about like hydrogen that is in enols. We say it is ppm here in this case. So carboxylic acid, it is exists 10 to 30. The different things like nitrogen and sulfur. Generally, solvent also affect the chemical. The increase the chemical shift of the hydrogen bonded with the heteroatom like oxygen, nitrogen, sulfur. In that case, the molecule may behave as you just monomeric and the chemical shift. And if very concentrated, then we say the hydrogen bonding, or we can say associated molecules there. So therefore, the chemical shift will increase. Temperature also affect. So with the increasing temperature, hydrogen bonding will be increased, and that's why the chemical shift as well as your this is what this phenol, which is 110. The hydrogen chemical shift is 10.45. If we make it a 10% solution, it had this hydrogen is 6.45. And similarly, if we go to 1%, it moves to different concentration as well as the pure your phenol. Similarly, we can also try to differentiate between the OH and N. You can see this one, and here the OH is also if we say n+1, so we'll say this hydrogen coupling with these two. So n+1 in neighbor there are two hydrogen. So we are having this hydrogen is coupling with this one. The methylene hydrogen will there is one hydrogen. It means this will which is present in the we see attached region will couple with the methylene hydrogen only when it is adding this then you won't find this coupling information in this case. I'm skipping this one. So this is about spin-spin interaction. We are talking about let me talk about this n+1 rule here. We can apply this n+1 rule, and we can say the two lines for each hydrogen. One in shows lines, and CS2 shows two lines in 112 tricolor, and this vicinal coupling, hydrogen attached with carbon, carbon attached with carbon, carbon. Remember these two hydrogen HA and HB, they are doublet. HA is coupling with HB and HB is coupling with HA. Coupling is in bonding electron, and in turn bond electrons, and there is CH bond electron, and finally with that of the hydrogen. Expression of the coupling is traveling via intervening bond. It is not in space. So here we can say that A is because if we consider as A and B is having two we are considering HB, so we can say two lines for HB because it is coupling with your this HA for HA and two lines for HB are being observed. So this is what we can say if this one is coupling with the intervening bonds are three. So if the intervening bonds goes on increasing, so attached with each other, but it is difficult to find out because we'll get only one singlet in the case of hydrogen. But in that tritium, and you can see increase in number of bonds between the two hydrogen, there is a decrease in hydrogen. I'm just skipping this one. So this slide I wish to interact with you in the sense that there is framework, no hydrogen nearby, so we have nearby we'll have the doublet because this is not interacting with hydrogen. This is coupling to the hydrogen which is shown red, so this is doublet and the intensity is 1:1. But there may be instead of one there may be two hydrogen, so that is as per so will this H red will but there may be the skeleton also like this. So in this skeleton you will find this black or you can say dark hydrogen or bold hydrogen. This way, so in nearby there are two hydrogen. So same rule. So but There is one hit in this case, in the sense that if this hydrogen is coupling with this hydrogen, and this hydrogen is coupling with this hydrogen, if the coupling is this the coupling of this hydrogen and coupling of these two hydrogen, there is triplet. Otherwise, if the coupling are different, then four line will be observed, and that will say here you will get red, and if they are different, you will in neighbor there are three hydrogen. There are three hydrogen like this one. So this one we will get a quartet, and if all are different, this one, and this, all three are different, then we will have lines, and those 8 lines are called doublet. Okay, so this is how one can try to know that what type of the skeleton is present based on the interest of NMR. Similarly, we will get the quintet and so on. We can try to see here in the different your type of the multiplicity and that two will have the triplet. Doublet. So coupling constants are different here, 12 hertz and 6 hertz. So it's the 4 lines with approximately this coupling constant they are same. That we are trying to analyze different types and what type of the substitution is present in the molecule, whether it is these are the appearance of the signal. Suppose this bracketed signal, if we are trying to there is a doublet, if so constant, it means the this one as well as this one. Whereas meta, this is doublet. If 2 meta, this is the triplet. And if we are this one hydrogen is there, we'll get this type of pattern. This is called doublet of doublet. And here in this 2 6 lines. In that case, so 6 lines or DT, like doublet of triplet. Okay, so these are the 6 lines. If so with these different I wish to about that the triplet, but this is in general. Okay, so if you are having acid added, you will find the same pattern is being observed, which is earlier here. Then if you are having highly pure ethanol, in that case, you will find the OH signal it is a triplet. If it is a triplet, it means that this oxygen is coupling this thing. And why it is not coupling in this one? This is because when acidic this ethanol is having acidic or some other impurity, in that case, hydrogen is not residing oxygen or reduction. That's why not we get a broad singlet. And will appear as a triplet. And the methyl hydrogen will appear as a triplet. There is no difference in this, but the CH2 here are being observed for methylene hydrogen. So how one can have the 8? Because when are coupling with this, so 2 lines, and each line will couple with these 3 hydrogen. So each line will split into 4 lines. So there will be total 8 lines. Megar's machine, the 8 lines are being observed. Okay, but how 5? That these 2 lines, they actually merge, and these 2 lines also merge, and these also with 1, this is 1, this is 1, and this one. So 5 lines are being observed. So for 8 lines is 5 and 8 lines, and for 5 lines we can say n plus n dash plus 1, so you will find 5 lines. So this is but there is for hydrogen, and that for methylene is your they're coupling each. For you can compare the your multiplicity chemical shift of ethyl acetate with that between these 2 types of the oxygen with that of the methylene, as well as here this oxygen is the methyl. So based on the, we can try to know the molecule, because the attachment of oxygen is here different. In cytophenol also, we have here different type of signal, that of orthohydrogen, and in monosubstituted we will the either 2:3 or 2:2:1. So one pattern is there, and to explain accordingly. So this it is there. So there are only, you will find in this one there are 3 signals for 1 and 2. So nitro groups are additionally electron. This is the that is trying as a doublet of doublet. So one can try to explain here easily if there are different to explain these molecules. This is that we are having the acetophenone. and night of the NMR was obtained except the methyl signal. Ensuring there are four signals, four hydrogens each differently. Now the question is a position or it is a meta position. Just this one that this is substitute orthonitrile substituted estrophenone. It is only two signal, not four signals. Four aromatic hydrogens. The most discrete signal will be one with your this one. So it because it is, and if it is so, one can try to exactly observe that what type of the company. So, madam, I just wish to complete questions, audience.
NMR स्पेक्ट्रोस्कोपी के इसमें any question? Very thankful to in a very easy manner. And all the academician and researcher are known that the NMR spectroscopy is a very for the database. So magnetic resonance also comes in the UG level. So very informative lecture.
Thank you very much. और इससे आगे ना 2D NMR है, तो 2D NMR बताया. I just took the basic thing. 2D NMR
हाँ सर, हाँ सर.
तो ये जो टीचर्स जो मान लो पढ़ाते हैं कॉलेजेस के अंदर, तो उनकी
सर ये यूजी में भी आता है सर, पीजी में भी और
यस यस
सेमेस्टर हो चाहे ईयरली स्कीम हो, तो उसमें ये आता है सर. तो ये बहुत इजी तरीके से आपने बताया सर. और डॉक्टर राजेंद्र सिंह सर, आर यू कनेक्टेड?
Yes, madam. I'm here.
Welcome, sir. हाँ. Welcome, sir.
Thank you, madam.
Now I welcome our speaker, Dr. Rajendra Singh Dayal, and now I'm going to describe the brief discussion of our speaker. And he did PhD at Chemistry Department, IIT Madras, and further he joined as a postdoctoral fellow at Dong University, Taiwan, and he contributed his research in the interesting area of synthesis and properties of boranes and chemistry. Atom of silver nanoclusters and their application in hydrogen evolution. Recently, he is working as an assistant professor in Central University of Punjab, Bathinda, and since 2015. And he has published result of research work in most prestigious journals and high impact factors like Journal of American Chemical Society, European journals in organic chemistry, etc. So many publications he has. And now and the behalf of teaching and research abilities, he received the Best Teacher Award, and from among the faculties at the Central University of Punjab, Batinda. And he also awarded a Young Scientist Award. To invite all the talk, development and application of nano clusters in nanoscience. So welcome, sir.
Yeah, good afternoon to all, and thank you, Madam Professor Meenu Mangal, for the nice and kind introductions. And I would like to also say thanks to other organizing committee member of this faculty development program. So let me share. My voice is audible to all. The slide. So slides are visible, madam? So and applications of science. So we are always discussing about the nanomaterials. So the nano cluster also come. It is the oldest known in 1950. However, in cluster science has been come in this field. So here today I have been included discuss that one. Usually the nowadays the coinage that old time metals to make the coinage. So coinage for like gold, copper, and silver. So these metals. So recently, the science community, nanoscience community, is a much focused on the synthesis of these coinage metals nanostructures. So here, how we can to know that. So let me talking about the nano clusters. So cluster you can see on your screen board that escape that is from nanometer, and then 1 nanometer, 10 nanometer, and 100 nanometer. So this then nanomaterial. So in the books, the transition from 0.1 to 0.9 nanometers. The so we become material. We and now atoms should be 10 to molecules known as a nano cluster. So nano cluster is the part of the nanomaterials. From the bulk material as well as from the molecular. So basic difference from 1 to 2 nano. And if the size go the or if we don't know, so here you can see the nano cluster. You can see the very nicely the structure and it is covered by the various kind of surface ligands. So here in the nano cluster of the nanomaterial, which is not so easy to get the crystal of a nanomaterial. So in this case, the nano from the structure, but in the nanoparticles which have the size beyond the 3 nanometer or 2 nanometer to 100 nanometers, so that you can see and that's we can come to know from the same or same images. So that will tell only about the what is the exact and what is the arrangement of the we know that nowadays there has been huge applications of the region. Why? Because we don't know the mechanism. And why we don't know the starting material of the nanomaterial, you cannot give a applications. So now the science, the science, because we know the exact structure of the nanomaterials via the nano clusters. How is it? So here I have taken a few type of methods. One is the bottom down method. So bottom up methods means we have to start from a single metal atom and ligand. Like method, photo reduction method, so in that we can just take the ligand and metal method and then it generate the nano clusters. What the size beyond the 3 nanometer to 100. So applications. So they are emerging in the various science, various then it giving the HER evolutions, hydrogen generations, and fuel cells. And if I talk about the bio contrast agents and cancer therapy, many more applications. And the degradation of the halocarbons, molecular sensors, and applications. We will grown up towards the hydrogen economy. Now we are very hungry for this hydrogen economy. Why? Because our basic need of energy. While the hydrocarbons are burning with oxygen, it will release the carbon dioxide, which is hydrogen with the oxygen, it giving the water, and we are getting the 3 times more energy and role in our daily challenging for us. Here you can see that however, if we increase it will be highly time same volume of the hydrogen if we of metal hydride form. So it is safe and easy to carry. So that's why metal hydride can play a great role to store the hydrogen. So copper hydride too, we will go to how it the copper hydride chemistry nano clusters. So in fact, hydride was discovered by how he synthesized copper sulfate and hypophosphoric acid. The location of was located and the distance 1.73 angstrom. But that there was 20 degrees Celsius is released the hydrogen and it cannot hold the hydrogen. So they showing the hypophosphoric nature. After that, in 1971, Osborne has been isolated first time hydride. That is a hexameric hydride. Is 6 atoms, 6 hydrogen and 6 ligands are there. So that was discovered, and if octahedron nuclei and stabilized by the phosphine. As I told you, it also associated with the 6 hydrogens. After that, suggested the pressure axis diffraction, and then that hydrides are located over the triangle face of this octahedron. Then at the same time, one scientist was and carbonyl compounds, and review has started in 2008 by using this single so they has to generate this copper in situ. Finally, to acquire the stable copper hydride, there has been also synthesized the bleached copper hydride. You can see by using the phosphine type of ligand and heterocyclic carbon ligands. And in 2009, the first time the LEU has been isolated a octanuclear copper hydride. There were the 8 copper atoms, and out of 8 copper atoms, the 4 copper atoms are framed in a tetrahedral form, and at the center of the tetrahedral there is the one hydrogen atom, and the further each triangle face of the tetrahedral core is further a copper atom. So overall, it generates a hydride-centered tetrahedral tetracapped 8 hydride, which is focused on stability. So how they come to know about this copper hydride? So for that, we need to take the copper salt and dithiphosphate ligand, 1/2 reaction in the room temperature, and it generate a copper 8 cluster. And the copper 8 have the cubic core. Copper atoms in cube. And these techniques, spectroscopic technique, and after that, they have been exposed this cubic copper 8 cluster with the fluorine atoms. And onwards that fluorine, chlorine, bromine, they have been introduced inside at the center of this cube. Introduce the hydrogen in the form of. So for that, if we take the cube, so we have been seen that in fluorine case that when fluorine comes situated at the center of the cube, it contains of the cube of the 8 copper atoms. But once we have been introduced the hydrogen atoms, what happens? This cube is converted into the tetrahedral. So it means the hydrogen atom is small atom, and it the alternative atoms and to introduce a new structure tetrahedral tetracore. If we use in case of the fluoride, the fluoride also has been released. By the neutron diffraction, it was confirmed the location of hydride at the center of the tetrahedral diselenophosphonates, xanthate, dithicarbamate, etc. So we take the copper salt, ligand, and borohydride in appropriate ratio, then we can isolate the copper 8 hydride. At this, we introduce if one equivalent borohydride, then one keeping copper atom get reduced to copper zinc and convert into copper hydride. We can generate the copper 8 hydride if we expose copper 7 with the one equivalent of copper salt. So in this series, if we add further borohydride, we should get the copper 6 and 5, but we are not getting in these situations. Then we have improved the amount of the first copper nano clusters stabilized by the 11 hydride. Improve it to 47% under the appropriate conditions, taking the liquid cost and the was done our 10 inches. Hello. So was calculated from the positive ESI mass analysis, and it clearly tell about the genes of the also found in that the adapt isotopic distribution and theoretical isotopic distribution of this molecular that we found that overlap matching of the experimental isotope distribution over the theoretical isotopic distributions. So it has been confirmed. Talk about the structure, which is one of the 19 Johnson kind of here down up, and one is the down one. So this one and this one. So they call the triangular. If you fit in between of them, it generates structure here. That is called bicupolar. In the form of this elongated triangular gyro. Here you can see the upper cupolar triangle. This cupola have the triangle and square planes. Down also have the triangle and square plane. So if triangle come in front of each other, square, but it goes reverse, like triangle come in front of the square face. In the structure of this copper 20 nano cluster, which stabilized by the this cluster, it found the 70. So it is fall in the nano. So it can call the nano cluster. It's metal, so it have the 20 copper atoms. Now if I, so out of 20 copper atoms, the 80 are encapsulated inside of this metallic core. Now if I talk about the locations within this metal core, we can see the triangular faces. Faces there on the upper cupola, and each triangle faces is covered or capped by a hydride ligand. You can see here the 3 hydride, and inside of this triangular cupola there is one hydrogen. That tetrahedral site is made by the upper these three copper atoms and one inside copper. The 4 more hydride atoms are situated within these upper cupolas, and similarly we have found 4 hydrides inside of the outside of this 4 hydrides in the cupolas. If we look at the 3 more hydrides, that hydrides are located in the square face is prism of the hexagonal prism. So here we have been found with the hexagonal prism, we are finding square faces, and the center of square faces is this cluster was further phosphorus. So phosphorus Nmr. We will try to understand how we can support this ligand. So here the ligand is the phosphorus. We found that 3 dithiophosphat ligands are surrounding around these upper cupolas, and down part, then there also we can found the 3 ligands. So along the C3 axis, the upper 3 ligands are similar type, and middle part, the hexagonal prism 3 ligands also should be the similar type but different from upper one, and down one also similar. But if I rotate this molecule along the C2 axis, which is perpendicular to C3 axis, then upper 3 ligand will actually down to the will be similar type. Those are different from 6, so 1:2 ratio. So here exactly we found in the phosphorus NMR the 2 peak and integration ratio also somehow is matched with this number. If I talk about the proton NMR of this compound, let me see how so this is the ligand here. You can see the phosphorus and one sulfur atom here, to another sulfur atom, two sulfur atom. This is the oxygen, and here the one CH proton and CH3. So isopropyl group is there. So the isopropyl group here the CH proton. So CH proton they here multiplies. So it's a consist with the result of the phosphorus NMR. And the methyl proton appear as a doublet at the 1.36 ppm. If we look at carefully in this NMR spectrum, then we are finding some small peak, broad peaks at the 2.8 ppm and minus 9.9 ppm. So that are related to the hydrides. In the triangle, upper cupola, the 3 triangle and each triangle kept by hydride. So here are the 3 hydrides along the C3 axis. These 3 hydrides are equally, and down also we can see 3 more hydrides. So if I rotate along the C2 axis, the upper 3 hydride on the triangles, they will exchange with the down one. So this type of hydride appear at the minus 0.9 ppm. And if I talk about within the hexagonal prism on C3 axis, they are also similar, and they observe at the same position at the 2.8 ppm. So now 2 more hydrides which is found in the upper cupola inside in the tetrahedral side and within tetrahedral side. So along, if you rotate the C2 axis, they are exchange between each other. They should be up around 1.4 ppm. In the proton NMR, unfortunately is overlap with the proton of isopropyl group. So here that we have been copper 20 D11 and 9 more hydride appear at the 1.4 ppm. So here integration ratio 3:2 × 6 integration ratio, we are getting the total 11 hydrides. So whole structure further also supported DFT study, and here the various bond length from the X-ray diffraction as well as DFT functional theory has been supported by the copper hydride and copper metallic distances, and also they have been calculated experimentally as well as from the DFT. The proton NMR has been shown. So if we look at the location of the hydride, so we observe here the first time in the metal hydride chemistry, we observe the first time a hydride in the square planar geometry, and in that, if we look at the hydride position, somehow above all 3 hydrides, they are founding above the plane. If we look at the molecule along the C3 axis, then also we can see that they are somehow side outline. So to find out is hydrogen storage material, the first condition is that material should be stable at the room temperature and it should evolve the hydrogen gas. Towards that, we have been done the variable temperature NMR, phosphorus as well proton NMR, And you can see that up to 60 degrees Celsius temperature, this compound is found. But at 65 degrees Celsius temperature, this compound start to decompose into another lower nuclei copper 7 hydride. At the same time, if we record the proton NMR, we are also observing the hydrogen gas coalition that is found at the 4.62 ppm. And same compound, then we thought that what should be if we, rather than heating, if we that compound died, so within 15 minutes this compound evolved the hydrogen gas. Then we are taking the another dichalcogen ligand. This is the dithiocarbamate. The sulfur, and this is carbon, nitrogen, and here it could be the alkyl groups or aromatic ring. So in that, we have been react the copper salt and ligand borohydride. Reaction was we are observing the yield 82% of a nano cluster copper 28 in the presence of 50 hydride and dicarbonate. It is described by the lower nucleated copper 8 hydride. So if I talk about the detail of structure of this compound, here you can see the whole molecule, more molecule structure, and the formula was, as I told you, that copper 28, 15 hydride and dithiocarbamate ligand. So now we will do the dissection of this compound to know that out of 28 copper atoms, the 24 copper atoms are framed in rhombic octahedron framework. And this frame is further stabilized by the 12 dithiocarbamate ligands. And each dithiocarbamate ligand have the 2 sulfur atoms. So there are total 24 sulfur atoms around this rhombic octahedron. And their position is framed in a truncated octahedron. You can see the yellow balls. If we look at carefully at the triangles of the it have the 8 triangles. Here you can see one triangle here in the back side, here back side, in the front one triangle, same triangles, 4 triangles here the downside, and so each triangle is shaped by a hydrides here. So and their location is mapped in a cube. If we look at inside of this rhombic octahedron, then we are finding that 6 more hydride that is called truncated hydride, and they are situated in the position of the octahedron. And if we go more inside of this cluster, then we are finding 4 copper atoms. There are 4 copper atoms, and they are framed in a tetrahedral core. And if we look at inside more and more in this one, then we are finding the center one hydride. So likely we have been assumed that there is a center one hydride, then a tetrahedral core, then a octahedron core, and rhombic octahedron copper 24, and 8 hydride truncate mu3h hydride in cubic form, and sulfur atoms 24 in the form of the truncated octahedron. So the most important is that is the rhombic octahedron. So rhombic octahedron is one of the 13 Archimedean polyhedron whose regular all vertices means we call the vertices the corner, each corner all the vertices. So it you can see the triangles, square faces, triangle, and so on. So out of 26 faces, the 8 faces found in triangle. You can see the triangles, and rest of these faces, but those square faces are different along with the rotational axis. Along the x and y z axis, the faces found that was faces along the axis. Here the C axis found that in the side similar. That is called the rhombic. cube octahedron. So our structure is more near to the generalized rhombic cube octahedron. And they are generating a cube octahedral geometry. So there are the 4 copper atoms, and 4 copper atoms can be accumulated in 2 ways. Either it can be accumulated in a square planar geometry or in the tetrahedral geometry. So that's why we are getting the disorder over the 12 positions of inside framed in the tetrahedral or in a for that we have the DFT guide, and it has been suggested that when 4 copper atoms are framed in the tetrahedral are most stable with least identity. So the location of hydrides within this cluster was supported from the proton and deuterium Nmr. So here you can see CS3, CS2, CS2, and the hydride was also observed in proton Nmr. The 8 hydride appear at minus 0.8 ppm, and the 6 was ppm, and 1 hydride at the center was observed the 1.2. Sample, and that is confirmed the presence of hydride. Either there are really 15 hydride is present deuteride, as well as there has been around 13.5 mass units. According to the formula, we should found the 15 difference mass unit, but we are not getting exactly. Why? Because whatever using our deuteride source are not 100% pure. So here you can see that how the 4 copper atoms are disordered at the center. These are the tetrahedral XYZ axis. Article in the inorganic chemistry. So later on, copper 28 nano cluster, and it was evolved the hydrogen gas while adding the acid. It evolved the hydrogen gas, and along with that, it was hydride, and copper 8 hydride can it also can exchange via the copper 7 hydride. So the presence of hydrogen atom in this copper nano cluster either is a hydridic nature. So for taken the deuteride sample, copper 28 hydrochloric acid, and it observed the triplet. A triplet observed So because H atom come from the this sample, so it have the hydrogen and sample was NMR, and there we are observing a doublet. So in the proton NMR, HD it has been confirmed that HD evolutions with the high character of. So if we look at a paper, nano clusters increase while adding the more reducing the 20 11 hydride and 9 dithiophosphate. What interesting nano cluster, that is copper 32. So briefly about the structure, it is little upper here you can see one cup bolas, down also a cup of 9, and there are the 14 copper atoms. So a rhombohedron we have found like a cube. You can see inside there is shaped by a copper atom that called rhombohedron. So a hexacaped rhombohedron of 14 copper atoms sandwiched between. If we look cupola, because you can come rather than triangle, so it is cupola. And the location of the types of the ligands were also along C2 axis, because it has a C2 axis along or C2H. So with that we can there should be the 4 type of what about the hydrides? Right, it found likely our copper 20. Also, hydride was observed at the hexacaped rhombohedron, and those are found in mu3 coordination mode. And we can also the cupola, upper cupola, and the centered hexacaped rhombohedron. And here also we square pyramid geometry. Similarly, hydride here. So we have been observed the 4 hydride peaks in that deuterium NMR, but it is not support the according to and the lower the temperature, low temperature NMR up to -60°C temperature, and we have been observed that here the one peak was observing at that is that is 4:2 ratio, and it reveals that of these symmetries, cupolas as well as the rhombohedron, and the 2 hydride at the cupolas remain unsplitted according to symmetry. And you can see that splitted according to this symmetry. Those are reveals the presence of hydride around the reveals the 4 types of ligand, but at the room temperature of phosphorus we have taken 60°C and observe that there is the 4 type of phosphorus which is confirmed by the and support the fully of the solid state. for the distance of the copper hydride and copper distance. It will computed at that, so I'm not going to talk about it in details. What will happen if we find with the reducing agent hydride? It going to be converted into rhombus shape pattern, also confirm the presence of these rhombus shape copper nanoparticles. So we cover 32 nanocluster, and finally it convert into the rhombus shape copper nanomaterials. It means while we are making the nanomaterial by copper hydride or metal hydrides as so taken this copper 20 hydride nanocluster and introduced this diselenophosphate ligand. So it have the two selenium atom, one phosphorus and two that a symmetric molecule. So understand the structure. So here for that I am telling you about the cuboctahedron geometry here. In this cuboctahedron triangle, and these both triangular planes are situated into they are also found in the staggered conformation. And center you can see a hexagonal plane of 6 hexagonal plane. They are they are found in a chain form. They are not in the place. So, or covered by so there if we and reveals the intrinsic chirality within this nanocluster. Further, the by the way was also on the Nmr U3H and with the mu3S type of ligand in this cluster. So this is a type of so look at the phosphorus NMR of this compound, then we are finding the 3 phosphorus peaks. So it definitely reveals that 3 type of ligand is there. But along with each type of phosphorus peak, interact with the phosphorus and it split into doublet. So both selenium atom of the phosphorus atom attached are different types. So it can be different. So that's what this one also, but it is found room temperature broader, but here while we so there are two diselenium ligand in this and both selenium atoms are different. So there's would show the 6 signals in this cluster. So whole work has been accumulated and published into the account chemical research of and 28 and 32. That is finally converted in copper 0 nanoparticles. There was also introduced the CO2 convert into formic acid by using copper 32 nano cluster at low ore potential, and proposed a mechanism for the TFT study. There has been about the via copper 8 hydride nanocluster and finally in the copper nanoparticles. So if I as we have discussed copper 20 hydride, 28 hydride and 32. So 32 copper hydride in presence of addition of the acid, it releases 20 in comparison of other stars. So we have also some unpublished data, so I'm not going to discuss here. The time is very short. And now I'm going to turn about the silver nanocluster chemistry. Let me talk briefly. 10 minutes I will take. So here also we can two and hydride centered copper 8 hydride. It would be interesting to interact with these. It's from the NMR, proton NMR of this cluster. So it means the hydrogen atom at the center of the tetrahedral tetra-capped silver atoms. And why it is giving so it is giving nonates. Why it is giving nonates? Because the hydrogen atom interact with the active nuclei of silver. Further, if we count the so the each peak of the nonate further split into the nonates. So we are getting nonate of nonates. Why? Because another nuclei of the silver 107 also interact with the proton or hydride within center. So because solid state showing the tetrahedral core, but 4 silver atoms are outside, but outside silver atoms out, and at the same time inner goes to out. Or it could be like that hydride may move within the tetra with the different tetrahedral site within the octanuclear AC8. So this spectrum for the silver 7 that is giving the octet, and you can see octet of octet. So very interesting this one to know that. I'm not going to talk. Higher nucleated silver hydride. So we are not getting the higher nucleated silver hydride, but rather than we get the silver nanocluster that was discovered in 2013. In 21. It also found the 8 electron superatom. Why superatom? Because it behaves like and talk about the AG21 frame, then we are founding a icosahedral. This AG12 silver atoms are framed in an icosahedral frame, and at the center one silver atom, and 8 silver atoms found the as a key atom on the triangle over this icosahedron. So this is the overall phosphate ligands. If we interact with one get reduced and we are getting silver 20. So here again I want to so very or XPS data also has been utilized. You can visible and absorption spectra. At the room temperature is showing the one peak, but at the lowering the temperature, it clearly supports the position of the ligands. Also, if we introduce 20 case 21, then what we found that Q equivalent or 1.5 equivalent gold, then central silver atom has been replaced by the gold. Yeah. So what role? So if we introduce in this silver nano cluster platinum, nowadays all the alloys. So here we have been discussed about the platinum silver superatomic alloys. So you can see this platinum atom is centered at the icosahedral. It is 8 electron species, and here you can see used a Y vertex that showing 16 electron species and 12. So they resemble the structure by two fused icosahedral and icosahedral are fused, given the electronic configuration 22. Complicated structure, so I'm not going to talk about details. And this one, the visible spectrum, so that is also differentiated by tech and these three molecules, and yeah, phosphorus NMR. And finally, I would like to acknowledge the final for the final support SKSRB, UGC grant, UGC startup grant, and I would like and Professor Warner Evangeline from Durban, South Africa, and Professor Rupesh Devan from and that you can see the working on this nano cluster science. And thank you for your kind.
Any question? ऐसे तो चैट बॉक्स में सब डाल रहे हैं ऑलरेडी.
Okay.
Very informative. So thank you, sir. I'm very thankful to Dr. Sir has explained the articles and the method of the of manipulations in cancer therapies, system, and the halocarbon degradations, hydrogen evolution, and we know the hydrogen is used as a fuel. And he also explained the spectral analysis of the complexes and also the information and convert the catalyst into the chiral system. Nano is an important tool in every field because it wide applications has already told. And if we change the particle size, now the property will be changed, and now the application will be changed. Precious time to us. Now I would like to thank you, sir.
Thank you.
Now I would like to invite Ms. Nirmala Bansal, another convener of this conference, FDP program, to conclude the session.
Everybody by convener Nirmala Bansal on the behalf of SPRTC College. Happy to conclude the successfully. Organized by Poddar International College in collaboration with SPRTC College. Today we have two lectures. One of Nmr Spectroscopy by Professor Rajendra Kumar, who through our life alcohols. Another lecture was by Dr. Rajendra Singh, Central University of Jharkhand. Gave us and appreciate knowledge on nanotechnology and clusters. So both the lectures are very informative, beneficial, and the academicians and researchers. Now, the feedback is available in the chat box. Fill and submit it. Thank you to all. Tomorrow again, session will start at 2:00, so you have to join 15 minutes before. Thank you all of us for giving us such a precious and important time. Thank you. Okay.
बेटा देते हैं किसे तो क्या करवा रहा है यार
ये चार स्विच कैमरा
स्विच कैम
Kindly fill the feedback form. Leave from the session. If you fill the form, if any problem you are facing, kindly box or you can mute your mic. डाल दिया मैंने ग्रुप में, आप देख लेना, ठीक है। हम नीचे चल सकती थी, कुछ चाहिए सूची से ये लिंक नहीं होगा, रिफ्रेश करेंगे तो लिंक आएगा। Also available at the FDP WhatsApp group. So thank you everyone for participating in the faculty development program. Tomorrow the session will start at the right time. So you can join before minutes.